Hi, welcome to this video on molecular geometry. So in this video, we're just going to talk about how specific Lewis dot structures lend molecules to be certain shapes. So there is a little memorization involved in this, but a lot of it is very logical. And so the shape of our molecule, we jump right in, is to minimize the electron pair repulsions. So when we draw the Lewis dot structure, what we're doing is we're showing where the lone pair of electrons versus the bonding electrons are. But we need to remember that all of our electrons are negatively charged. So they have one pair of electrons that have opposite spins can occupy the same orbital, but individual pairs of electrons are going to create repulsions with each other. Not enough to break the bond, but enough for them to push away from each other and create specific shapes. So that's what we mean by the molecular shape, is minimizing those electron pair repulsions. It creates a shape that gets them as far apart as possible. So VSEPR is valence shell electron pair repulsion theory. That's what that stands for. And so basically it's just that the molecular shape is going to change as you change how many sigma bonds and lone pairs are on the central atom, because that's going to change the repulsion. So we have different things, different types of geometry. So some of this is going to be different than first year chem. So one is we have electron geometry. Electron geometry looks at all of our lone pairs and bonds and takes them all into account. So it's looking at all spatial regions around the atom, not taking into whereas molecular geometry says don't be confused with molecular geometry. In molecular geometry, we ignore lone pair electrons, even though they are having an effect on what the shape looks like. Electron pair geometry is basically how many things are around the center. And I just realized that geometry spelled wrong. Should be an E right there. All right, so when I have two pairs of anything, so in this case, like a sigma bond and a lone pair, right? Anytime you have two things around your central atom, it could be two sigma bonds, whatever it is, two things, that's going to be a linear electron geometry. So typically what we would normally think of with that is, let's say I have something that's double, like single bonded like this or whatever. So that's just two things around my center. That's going to be linear. So things like beryllium that has an exception to the octet rule and doesn't get any extra bonds, that's going to be considered, just has the two sigma bonds. That would be considered linear. We can also have CO2, which has two double bonds on each side. We're only looking at those sigma bond connections. And so since it just has the sigma bonds, that makes it linear as well. If I have three, either sigma bond or lone pairs on my central atom, so three things, it's going to be trigonal planar. So that would be like I have an atom, and then let's say I've got just three bonded atoms off of it. So it could be the exception like boron, but it could also be something that has a double bonded, like a CO3 or something, where it has a double bonded oxygen would also work. It could also be a bent molecule would also work if it only had one lone pair on it. Tetrahedral is probably the most common one that we're going to see. That's when you have four things around the center. The 5 is going to be expanded octets, which is trigonal bipyramidal, and 6 is octahedral. So both of these are expanded octets, meaning they're going to have more than four pairs of things around the center. So electron geometry is looking at all of the electrons around the center, not just ignoring lone pairs and how things are bonded. So it's a little bit more, there's a little more overlap there. So with the VSEPR model and the molecular shape, we also have to understand molecular geometry. So molecular geometry is the arrangement in space of the atoms that are bonded. So we're only focusing on the atoms, not all of the lone pairs. So lone pairs have a different repulsion since they're experiencing an attraction or pull from one nucleus as opposed to two nuclei. So they tend to take up more space around an atom. They do affect the molecular geometry, but a lot of times we ignore them when we're talking about it. So each lone pair or bond is going to repel other lone pairs. And they try to avoid each other, making it as wide as angle as it possibly can. And we typically focus on this with the S and P block elements. The transition elements are very difficult because there's a lot of exceptions to the octet rule within transition elements. And so they do some weird stuff with their structures and things like that. So down here, I've got some molecular shapes for central atoms that have normal. So we're going to focus on normal octet valence structures. We're going to do those first. So when you have normal valence, we would have no more than four structural pairs. That means I can have, let's say, 3 sigma bonds and 1 lone pair, right? Or I could have 4 sigma bonds, like a tetrahedral. Or I could have, 2 sigma bonds and 2 lone pairs, whatever it is. So you've got 4 things around the center, as long as the atom is obeying the octet rule. If there are no lone pairs are present on the center, then basically your molecular and electronic geometry are going to be the same. If lone pairs are on the center, then that's going to change the two, because as soon as you put lone pairs on the center, you're going to distort the structure. And so what we see in terms of atom arrangement is going to be different. It's not evenly symmetrically spaced all the way around that central atom. So we tend to see when there's no lone pairs present, a lot of times I will say that is what we call symmetrical. There's symmetry there, because everything's going to arrange itself evenly all the way around. But as soon as you put the lone pairs on there, it creates an asymmetry to the structure, and then we don't have the same electron geometry and molecular geometry names. We ignore the lone pairs after we figure out our angles, so the lone pairs are not what we use to figure out what the molecular geometry is. All right, so let's look at some examples. So first we want to identify sigma and pi bonds just to practice that. And then we're going to look at the electron geometry and molecular geometry below. So I kind of drew both. I had this, and I didn't draw them. I shouldn't take credit for that. What I did was I showed some images that show the shapes, but also show the Lewis dot structure so you could kind of see. So over here on the left, you're going to see I've got methane. So I've got the structure so you can kind of see what it is, but I've also got the Lewis dot structure right below it. So what you're going to notice is there's no lone pairs on the center. On the carbon, right? So there's no lone pairs on the carbon there. And so we've got 4 things around the center. So you've got 4 sigma bonds, right? So that's what that is. So 4 sigma bonds means there's no lone pairs to create any kind of distortion. And so since there's no lone pairs, we would say 4 lone pairs would be tetrahedral for electron geometry, because it's got 4 pairs of electrons around the center. And since there's no lone pairs, that is the same as the electron and molecular geometry. So tetrahedral for both, okay, because there's no lone pairs on the center. So that's really easy because we can see easily that, the shape or whatever is a tetrahedral. It creates something with 4 sides. We're going to work on these a little bit in class too. All right, the next one you'll see is NH3. I'm going to change colors so you can see what I'm doing a little bit more. So with NH3, there's a lone pair up here on the center, right? And so that lone pair on that central nitrogen, when we look at this one up at the top, we can see, the one at the bottom with the Lewis dot structure, I can see a sigma bond, a sigma bond, a sigma bond, right? And then, so I've got 3 sigma bonds. So 3 sigma bonds, and I got 1 lone pair. So notice this still has 4 things, so the electron geometry is still tetrahedral when I look at it. So electron geometry is still tetrahedral, but because there's still 4 things around the center. But when I look at the actual shape, we do not see that lone pair. So what we end up seeing is with the shape is we just see how the atoms are arranged. Oh, I guess it would be this one over here. I tried to drop it off. You would just see how the atoms are rearranged. And so when we look at how the atoms are rearranged, what we're seeing is that lone pair on the center creates basically a distortion or an asymmetrical molecule. And so when we do that, our molecular geometry, so molecular geometry for this one is going to be trigonal pyramidal. So it creates a little pyramid. And there's a page up a little bit later that lists them all. Then we can see, we look at put the water molecule in here. So with the water molecule, let me change to another color. So with our water molecule over here on the right, we can see that structurally or spatially, there's lone pairs, right? So there's 2 lone pairs on the water molecule that give it its distortion or creates that octet. So what we're going to see here on the water molecule is you've got a sigma and a sigma. So in that case, you've got 2 sigma bonds and 2 lone pairs. So my electron geometry, because I have 4 things, is still going to be tetrahedral. But when I look at the molecular geometry, I'm ignoring those lone pairs that you see. So then we end up with a structure that looks just like this one over here on the right. So the molecular geometry for these with 2 atoms is bent. So you probably remember that for water because it's a specific one we have to know. So the molecular geometry with the lone pairs is different than the electron geometry of how many things are around the center. So there is a little bit of memorization with this when you're looking through these. So let's look at some more. Okay, so to determine the molecular geometry, right, the first thing you really want to do is sketch the Lewis dot structure. You don't want to skip that. It's really important that you draw that because it depends on whether or not there are lone pairs on the center. So if you skip that and you don't actually draw a correct Lewis dot structure, there may be lone pairs on the center or there may be none, and it could affect whatever you're predicting for the molecular geometry. So the first thing you want to do is describe the electron geometry, and that would be the total pairs around the center. And then focus on the atoms and where they are, ignoring the lone pairs to figure out your molecular geometry of what's happening. You can also figure out the bond angles with that as well. Molecular shapes for atoms with expanded octets are a little trickier because you can replace some of those extra atoms in the expanded octet with lone pairs. So it creates different shapes. So for example, on this first one up here on the left, there's 5 things on the center. But if I look at this, I've got a sigma, a sigma, a sigma, and a sigma. And then you've got a lone pair and a lone pair, right? So this has 4 sigma bonds. So then you can see what the structure looks like because we ignore those. So since there are 6 things around the center, those 6 things, we would say that that's octahedral, right? But when I actually look at the molecule shape, I'm going to ignore the lone pairs. So when I ignore those, what we really have, what the molecular geometry is a seesaw. So hopefully you kind of see the little seesaw right here, right? Yes, and people can sit on it. My little side person sits on it. Ignore the fact that I can't draw a person on this sideways. But that's a seesaw shape because those 2 lone pairs are going to be on the same side, and so it's going to end up making them seesawed. All right, what about the one at the bottom? So this one right below it, do you see it also has 6 things? So we've got 4 sigma bonds again, right? Did I do that right? 4 sigma? Okay. So I've got 4 sigma bonds, and then I've got 2 lone pairs. Oh, did I do that? Did I count those wrong before? 1, 2, 3, 4, 5, 6. No, I did it right. And so we've got a lone pair and a lone pair, right? So on this one, we're going to see it be octahedral again, okay? But when that lone pair on the top and bottom is removed, do you see that it has 4 things going around the center? This becomes what we call square planar. All right. So we've got the 4 things. So the top and bottom were what was removed. So it looks a little different than what we saw based on what was removed in the previous one. All right. The one over here on the right shows different ones as well, but these are all, if you notice on them, let me change my color again. We've got 5 things. So this has a sigma, and then lone pair, lone pair, lone pair, right? These all have 5 things. So these are all for an electron geometry. They're all going to be trigonal bipyramidal. All right, but their molecular geometries are going to be different depending on the atoms that are present. So for example, when I look at this one, I just see that. So on that shape, I'm trying to look at what it is. They would be flat. I'm losing my mind on this one. Hold on one sec. I feel like that is a bent shape, but I'm not positive. Pretty sure it's bent. That one's different. And so this is showing you the same spatial arrangement right here. Again, it ends up being bent. Okay, but this one, do you see how this one lines up in a straight line up and down? That one's actually linear. So we have to look at kind of which of the shapes or how they lose them to determine what their overall shape ends up being. So we see linear because we're not seeing any of those lone pairs that are present. All right. So expanded octets, you have to draw it, and then you have to look at where are those, what's happening with those bonding locations, those additional bonding locations. All right, so here's one where it says when phosphorus reacts with excess chlorine, the compound phosphorus pentachloride is formed. In the gaseous and liquid states, the substance consists of PCl5 molecules, but in the solid state, it has a 1-to-1 mixture of PCl. I feel like that's supposed to be a 4 plus 1. I think it just, my formatting got jacked up. So I think this is supposed to be PCl4 plus, like it lost one. And then PCl, I think this one's supposed to be PCl3. I don't know, PCl6 minus, my bad. Predict the geometric structures of PCl5, PCl4 plus, and PCl6 minus. So what we want to do is obviously draw them. So PCl5 is very easy because we know that it's going to be the gaseous state, it's going to be an expanded octet. So when we add all those up, you've got 5. So phosphorus is going to have 5 valence electrons. So 5 plus, and then you're going to have, so I always do one of my atoms up, one of my atoms down, and then the other atoms coming, oh, I drew that bad, off the center, kind of making a circle. It'll help you kind of make your structure look a little better. So then it'll be chlorine and then chlorine. So we draw our structures first. So all of these are probably going to end up being the same electron geometry. It's going to be their molecular geometry that's going to be different. But we're going to double check. So I've got 5 times 7. So that's going to be 40 electrons in this structure. So 40 electrons is 20 pairs. I've already drawn in 5 sigma bonds. So that's going to leave me with 15, which means each one of them, I make this a little bigger. So each one of them is going to get an octet in lone pairs. So I'm going to draw those in. All right. And all right, so that one looks just like that. So when I go to set this one or to predict this one, right, on the prediction here, my electron geometry is going to be, because there's there's 5 things, is going to be trigonal bipyramidal because of the 5 things. And because there's no lone pairs, it would also equal the molecular geometry. Okay, so those 2 things are going to be the same. Now I'm going to look at the PCl4 plus. So let's see how that one comes out. I'm going to do it in a different color. So PCl, I'm still going to have phosphorus in the middle. I'm going to do my chlorine up and then chlorine down, and then I'll do chlorines coming off either side. All right, so we're going to add up all of our valence electrons here. Pretend my chlorines look a little nicer than they do. So you're going to have 5 for your phosphorus, and then you're going to have 4 times 7. And then don't forget that plus 1 is really a minus 1. So 28 is going to be 33. Minus 1 would be 32 electrons. Oops. Sorry, I just accidentally clicked on something. So that's going to be 32 electrons. So that's 16 pairs, and we drew in 4 already. So that means that with those 16 minus 4 leaves me 12. So I'm going to do dots on those. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in this one, this is not going to be an expanded octet. So when we compare this one, we would also, I don't want to forget, we also put brackets around it, and we would put a plus 1 over here. So this is not going to be expanded octet. So it lost the chlorine and was deficient in one electron so that it could make the structure work. So in this case, my electron geometry here is 4 things around the center. That's going to be tetrahedral. And since there's still 4 things around the center and no lone pair, that electron geometry is the same as the molecular geometry. And double check me because I am doing this on the fly, so if I made a mistake, please tell me. But I'm pretty sure I did that correctly. So if I double check, if I'm ever not sure, the easiest thing to do is to go back through and double check your number of electrons. So I know I should have 16 pairs. So if I go back, I've got 4, 4, 4, and 4 on all of my chlorines. So that means I know that I have the 16 electrons I needed. And then you can always double check your math too, just in case. So I know that I had 4 chlorines that were times 7, so that's 28. So that's going to be 33 minus 1. All right, the other one, I'm going to scooch over here to give myself some room because I didn't. So this last one, PCl6 minus, right? So again, I'm going to have my phosphorus in the middle, and I'm going to have 6 chlorines. So I'm going to have 1 chlorine up, 1 chlorine down, and now I'm going to have 4 chlorines around the center to make them fit. Cl, Cl. So when I do my math, I'm going to have 5, and now I'm going to have 6 times 7. And the -1 means plus 1, it gained 1. So I've got basically 6 times 8, which is 48, right? I just did that in my head. But so that's going to be 24 pairs. So obviously I've already got 6 sigma bonds in there. So 24 minus 6 is going to leave me with 18. So when I go to start filling in my lone pair electrons, I've got 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So everything ends up with its octet. So I know that that is satisfied. Okay. It's an ion, so I want to make sure I draw my brackets like I did before with a -1. Okay. So then my electron geometry on this one, notice no lone pairs again, is going to be the same as the molecular geometry. Those are going to be the same. And so since there's 6 things around the center, that one's going to be octahedral. All right. So the different shapes, or not shapes, the different states of them in the mixture could have something to do with the lone pairs that we're seeing, but who knows? So comparatively, they all look a little bit similar, but once we draw the structure, we can identify what their electron geometries are and what their molecular geometries are. Remember, if you put lone pairs on the center, your electron geometry and your molecular geometry will vary. All right, so I inserted this table into your notes because I really love it. It kind of hits everything you could ever possibly think of. It's got your electron geometry, it's got your molecular geometry, which is the difference, right? And it's got specific examples of ones that we've probably already done in our notes so you could see. And I like that it shows kind of the 3D shape so you can help you see what the shape would look like without lone pairs on the center. So keep in mind that 3D shape is what the molecule shape was. That's basically explaining where the geometry of the atoms are, not including the electron pairs. It also has the bond angles. There's a lot to know. So you do have to know this. Like, you have to memorize this for the test. And it's important to be able to recognize them, but you kind of get good at them when you look at your shapes. So for example, something that is a linear is going to be a straight line. So notice when you look at that, the atoms line up. So if it's a geometry that's going to be linear, the atoms should be lining up exactly. When I look at something that has 3 things around the center, they're going to evenly divide that space. And so your bond angle, it's trigonal because it's got 3 atoms around the center. This bond angle is going to split an entire circle, which is 360. So if I split that, that makes each one 120 degrees. So students are always like, I can't figure out the bond angles. That's really what it is. The bond angle of the linear is a straight line, which is 180. For something that has 1 lone pair on the center, which is what you see in this next one, that 1 lone pair actually creates a bond angle. It doesn't split it evenly. The lone pairs take up more space. So therefore, the bond angle between the atoms is going to decrease. So that's why it's a little less than 120 instead of being exactly 120. But remember, we can't see, don't draw this on your paper, but you can't see that lone pair. So that's where this bent structure is coming from, because we can't see the lone pair. We just see the atoms lined up. With 4 things around the center, you get the tetrahedral. So in that case, you got 4 sigma bonds. So we can easily see those 4 sigma bonds. They spread out. And so what ends up happening is the angle is not 120. It just, the way that it spatially rearranges 3-dimensionally, becomes 109.5. But then a trigonal pyramid, where we put the lone pair on there, again, remember, spatially pushes away. We can't visibly see that, but it pushes these closer together. So that's why it's 107.5 for the trigonal pyramid. So the ammonia, the NH3, with that lone pair on the center or trigonal pyramid, is going to have a bond angle of 107.5. When I put 2 lone pairs on the center, I'm still bent, but the angle becomes even smaller to 104.5 for water or something that has 2 lone pairs on the center like that. And then you could see all of the expanded octets, which are brand new. So these ones that I just went over, those are ones that we talked about in first year. But these expanded octets get a little complicated because you have to be able to look at the whole structure. So with 5 things on the center, what we can see, so for example, here we've got the trigonal pyramidal because it has 5 things on the center. And with no lone pairs, that's going to be the same. But notice what happens when you take electrons away. Each time you take an atom away, not electrons, each time you take an atom away and replace it with a lone pair, it replaces it around the circular portion right here that's going this way. This is almost kind of what you see. But then what happens is you still got your straight piece, but now all of a sudden you just have these little pieces. That's that seesaw shape we talked about. But a lot of times you're going to see it's going to look like this, because I always take away the center part. So you end up, it looks sideways like what we saw in the notes earlier, right? So we take away one of those center ones. So with the trigonal pyramidal, each time you remove an atom and replace it with a lone pair, you take them from the center, the ones that are rotating around the center like this, leaving behind the straight up and down, or the linear piece. So then when I replace it with two lone pairs, right, then all of a sudden I don't see this part anymore, and now it just becomes a T. And so that's going to be 90 degrees for its angle. And then for the three lone pairs around the center, we don't see the center at all anymore. And so now it's just lined up in a straight, nice, perfect line. So the bond angle becomes 180. Our octahedral with 6 things around the center works very similar. So when we look at the octahedral, let me switch to another color. Let's go with yellow. All right, so when we switch to another color, we look at the octahedral is when anytime I have 6 things around the center. So that would be my electron, and since there's no lone pairs in this one, they're all the same. So again, it lines up like this, except the difference is now it's not circling around, it's making kind of like a square around. So what we see happen here, when we remove, to help you see this, the shape a little better, when you remove lone pairs, you remove one of the ups and downs. So we remove this one, and so what we see is still this shape right here, but it's coming upward, right? And so that's where they get the square pyramid, because it's very similar to the trigonal pyramidal, except now it's a square base instead of a 3 on the base. And then if I take away another atom and make 2 lone pairs, we can't see those lone pairs on the top and bottom. And so then all we have is a square, flat square, which is square planar. So that's kind of where those names come from. But you do need to work on knowing these. You'll get better at them the more practice you do with them. You'll start recognizing them. But I would say that probably the most difficult ones or challenging ones are the expanded octet ones, because there's a lot of variation of what it can do. All right, so that kind of sums up our molecular geometry notes. So things you need to make sure you're really understanding is the difference between electron pair geometry, which is looking at all bonds and lone pairs around the center, and molecular geometry, which is ignoring the lone pairs and only looking how the atoms are spatially arranged. And then you really need to start working on getting to know or memorizing these. Flashcards, we'll do a little bit in a class where you get to get the model kits out and look at the models, but you really have to make the Lewis dot structures make sense. So a lot of times I'll redraw my Lewis dot structures so that they'll fit with what the shape should be, like when I have lone pairs on the center, pushing the atoms closer or down, and trying to show that shape a little bit, because it'll help when you draw your Lewis dot structures if you're drawing them spatially correctly, because then that'll help you identify your molecular geometry and your angles a little better. The other thing to help you with the angle memorizations is if you know what all of the shapes and the angles are with no lone pairs on the center atom, when you change out an atom with a lone pair, it's going to decrease that angle. So that'll help you remember it a little bit better. And it requires a little less memorization that way. So anyways, just work on studying these, but you're already, ahead of the game because you did the notes. So you'll come to class and we're going to do some more practice on this.